started. Again, the link to the software is in the chat, and you can download that and apply the temporary license key with all the features enabled. Today's webinar will be looking at the new features of ObserVIEW 22.1. My name is Ryan Quillette. I'm the Product Development Manager at VR. And let's take a look at some features that will apply to everyday use cases. Specifically, I'm going to be covering FDS for doing real-time fatigue measurement, and also for doing post-process test development. We'll look at SRS, or shock response spectrum. We're going to look at converting time waveforms to velocity or displacement. Also playing back data audibly through speakers, so you can identify patterns in the data through audio. And we can compare traces against a tolerance line that'll easily point out where data is above or below a selected line. And as you can see, there's a large list of other features. I'm not going to get into all of them. One other one that we'll get to is preview features like math traces for frequency graphs. And I'll show you how to enable technology preview features right now. So in the settings of the application, there's a technology preview section, and we can turn on math traces, 3D graphs, time filtering, and doing a linear average of FFTs. Okay. We'll be taking a look at some data collected on a racetrack with a Porsche. I'm going to load up the map and some video so you can get some context. Here's the map, and then here's the track, and you can see relative speed through the track. We go anywhere from 36 miles per hour up to 109 miles per hour. So I'll put that off to the side. And then we also have the in-cabin view of the driver. Put that off to the side, and then arrange this. And I'll just do a little bit of a playthrough so you can get an idea for what the track is like. And we'll skip ahead here so you can see on the GPS we go through different spots. Here it's going to be exiting this turn and going into a long straightaway. So right now it's in the slower section and it's accelerating. And here we are going down the straightaway, going very fast. Alright, so that gives you an idea for what we're looking at. Let's take a look and convert the acceleration waveform we've been looking at over to displacement. So to do that, I can just right-click on the y-axis of a time graph, and I can pick displacement. It's pretty simple. And now the cool thing with displacement is that it kind of removes some of the high frequency noise from the signal. It makes it easier to see the macro movement of the vehicle. So in the chassis in the vertical direction, we can basically see the suspension moving through some bumps here as it's going down that high-speed section. I've got the corner frequency set to 10 Hertz here, and that's an important thing to point out. I think our default is 3 Hertz. So here's 3 Hertz, and I don't know if you saw that, but it does change the amplitude quite a bit. So I'll put this back to 10. So that's 10 Hertz corner frequency for the integration that we're doing from acceleration to velocity to displacement. And if I set this down to 3 Hertz, then we get more displacement coming through. So Sensors have specified working range that they're calibrated for, and most of the IEPE sensors that we tend to use have a working range of above 3 hertz up to 10,000 hertz, and that varies based on the sensor. There are, of course, some low frequency sensors that go all the way down to 0 hertz. But if you have too low of a corner frequency, let's say 1 hertz, you'll get very, very large displacements that don't match reality. So what I recommend is looking at your spec sheet for the sensor and then putting in the number that it has for the minimum frequency that's in specification. Now, the other thing I recommend is when comparing time data between different recordings to always use the same integration corner frequency. That'll make things at least comparable. So that is what the displacement looks like. I'll also point out there's an easy way to add a displacement graph beyond just right-clicking on the y-axis. You can also just do add graph, add displacement waveform, and that will do the same thing. If you needed to, you could also look at velocity. And now we're looking at the velocity versus time. Okay. Now you can also do this acceleration velocity displacement conversion on the power spectral density graph. So if I click on this power spectral density graph and I choose, if I right click on the y-axis of it and then I choose displacement, I can look at the displacement spectral density. Now this file has a lot of low frequency displacement in it because of all of the suspension movement of the vehicle, but there it is if you need to see it. We'll be looking at another file here very shortly that is a little bit cleaner environment. It's run on a shaker in a controlled environment, not like this one. So let's go take a look at that. These files that I'm showing, by the way, are all included in the software in the example folder. So if I open this, it will open it up in my file browser, and you'll see the path to this is the C drive, ObserVIEW, resources, VFW files. And in here you'll find a bunch of useful example files to pick from. But it also will show up in this main page. So let's open up the vertical beam excitation. Okay, so with the vertical beam, we have a random test being run with a stinger attached to a beam that's hung from the ceiling. And then what we see with this is a lot of freely vibrating mode shapes on the beam, so we get to see each resonance frequency of the beam very, very clearly. The test, if I were to enter this into vibration view, would give me an estimated displacement. I'm not going to go through that process right now, but here we can take the recording of the test and easily convert it to displacement and learn some things from the displacement waveform that maybe we wouldn't learn from the acceleration waveform. Okay, so here's the raw acceleration of this random test. You can see that it's going up to 55 Gs here, in some places 70 Gs, so relatively high, right? And then we down in the PSD, we can see there's looking to be a resonance at 25 hertz and at 99.5 hertz, 165, and then a large one here at 621. So let's take a look at the time data and see if we can correlate the resonances that we're seeing in frequency domain to waveform spikes that we see in the time domain. If I were to take this here and then go down to this point here, so this is a delta cursor I'm using, you can see that the delta time is 0.0016 seconds and the frequency is 630 hertz. So that 630 hertz is probably this resonance right here. Okay, so that's pretty interesting to see. Now, what happens if I were to convert this data to displacement? So let's turn displacement on, zoom out a little bit. Now in the displacement, we've got some larger, slower updating peaks here. So let's take a look at this one here. Okay, so we'll look at the delta between that, and this is 0.038 with a frequency of 26 hertz. Now that 26 hertz is this frequency right here, much lower. Sorry, I'll annotate it here for you. So 26 hertz about right there. So that is the power of using a displacement conversion on time data. It basically will de-emphasize the high frequencies and make it much easier to see low frequency vibration in the time waveform. And this can be helpful for diagnostics and looking at things over time. And you can also see these low frequency pulses that are happening. If you were to just watch the shaker as it's doing the test, what you're seeing with your eyes is most likely the low frequency movements, not the high frequency movements. So this is what you'd be seeing with your eyes. And I'll convert that back to acceleration, and look, you can barely see it. And so it's a fun, useful diagnostic tool to use. You can learn it's like a whole nother way of looking at the data when you start to filter it out and look at the lower frequencies rather than the high frequencies. So that's this file, and that's all I have for the acceleration, velocity, and displacement time conversion. That is a feature that's included in the advanced license of the software. So that would be this one here. And that also includes resampling and filtering and doing octave band analysis. Next, we're going to move on to doing some audio playback. So audio playback is included in the advanced license also. First, we're going to listen again to this Gingerman Raceway video, recording really. And rather than looking at the video and hearing the audio from the video, we're going to turn on the audio playback from one of the sensors. Okay, so let's take a listen to this straightaway section right here. Maybe we're accelerating through it. Okay, and we're going to do replay and then audio channels. And then I want to listen to the chassis in the vertical direction. Okay, so I'm going to be converting the acceleration waveform to audio. So that was the accelerometer on the chassis in the vertical direction actually converted over to audio. I also have the microphone here that we can listen to independent of that, so we'll play that back. Let's see, go back a little ways. So what's interesting about the microphone is that we can hear other vehicles around the car, and we can hear the exhaust a lot more. So other vehicles' audio obviously isn't being transmitted into the frame of the car as much. So if you want to listen into just one vehicle, it's actually pretty practical to take the accelerometer that's mounted, hard mounted to the chassis, and take a listen to it. It's also very interesting to hear all of the RPM information from the engine making its way into our accelerometer recording. And if we take a look at the spectrogram of this, we can also see the engine kind of cycling through gears. Okay, so if I change this, I think I can get us a little bit better picture. Yep, there we go. So I'll turn on the, all right. So these lines here, they're kind of going off on an angle. That's the engine cycling through gears and revving, through its power band and then resetting. So this would be like one gear right here up to this point, and then it resets, and then another gear, and then it resets, and then another. So that's how that works. And we can take a look at it in 3D also to see a little bit better view of that. Pretty interesting. Okay, we'll turn that off. And now let's take a look at another file where we can listen into the audio and learn a lot. This is firearm burst, which is actually a machine gun firing. We recorded this with the observer. So I'll reset this to be a little bit smaller window, and then we will play back the audio. So I'll put that on repeat. So very fast firing. One super interesting way to analyze this is to slow it down a lot, like 1/20th the speed. So we'll play it back now at slow motion. So that was pretty interesting. You could actually hear the bullet firing, then the slide moving backwards, then the slide moving back forward and engaging the next bullet to fire, and then firing that bullet, and then repeating that process 4 times. So those are the kind of things that we can learn by analyzing the audio. In the audio, you can also turn equalization on and off. So what the equalizer does is it lets you listen into specific frequencies or detune certain frequencies. And I'll show you a little example of that. So I'm going to do all cut. What all cut is doing is it's dropping all of these down in the EQ, and then I'm going to raise up just, let's say, 250 hertz, so we can listen to just what 250 hertz sounds like. Play that through. So that was interesting, and then you could also listen to this. Now, when we are playing it back in slow motion like that, the pitch is actually being shifted, so you have to bear that in mind with what the EQ is doing there. But it is, again, a pretty helpful diagnostic tool, so you could listen into specific frequency ranges. For instance, I could listen into just the engine RPM frequency, or I could turn off the engine RPM frequency and try to listen to the road noise from the suspension. So that's audio playback. Now let's take a look at doing some live and post-process work with fatigue damage spectrum. Again, I'll bring up the GPS view, and this is very helpful for me so that I can tell where in the track I am analyzing data. What I'm going to do is go to this straightaway here. We're going to analyze the fatigue damage potential for just this northbound straightaway. So I will add in a FDS plot. And with the FDS, what we're doing is converting the time waveform data into a potential damage spectrum of data. And when we have the data in the damage spectrum, we can weight the damage to be higher or lower with simple multiplication. We can also sum fatigues relative to one another. So it gives us a lot of flexibility in how we can manipulate the data and how we can compare one part of a recording to another part of a recording, or we could compare one environment to another environment. Okay. Let's see if I can move this map to a spot off to the side. Okay. So this part has a fatigue damage of this. We'll take a look at just the chassis in the vertical direction to make this a little simpler. I'm going to increase the analysis bands so we have a little bit more detailed view. Turn that off quick. Okay. So this represents the potential fatigue damage for this northbound part. I'm going to copy and paste it. Just Control C and Control V, and then rename this northbound high speed. Now I'm going to take and move this across, and we're going to find a section of track that's a little bit slower, like this. So all this right here is some switchbacks and stuff like that, where the vehicle is forced to be moving slower. Right there to that point. So you can see it's all this section here. And it's a longer stretch of data, but intuitively it's going to be a little less damage because it's going not as fast. So let's copy and paste this. And we're going to call this the slow section. And I'm going to take this high-speed one, and I'm going to right-click on it and say this is my tolerance min. What that's going to do is compare all of the other traces on this plot to this tolerance line. Or actually, it's going to compare this one here, this one to that line. So we can see when we compare these that the and I'm going to mark this as bold actually also, so it's easier to follow. So get this to be a little bit thicker. Alright, so the red line is our high-speed section where we were going north, and then this line here, or the gray line, is that slower section, but it's a longer section. And the way we will read this is anywhere that this chassis vertical current section, the slow section, is higher in potential damage, we're going to be green. Anywhere where it's lower, we're going to be red. And I'm going to move this back a little bit so it is lower, and then you can see how that'll build up over time as we play through this. So at this point, where we have less data collected, the fatigue damage is lower. And now as I play this file through, you'll see that the fatigue damage starts to accumulate, and even the slower section is going to start passing the potential damage of the high-speed vertical section. So as it starts to turn green, that's where it's going above. And I can speed that up to make it a little faster. Alright, pause it there. So kind of a cool way to compare two different sections of the track that are very different from one another, but we can then compare the potential for damage in between those sections. We could also compare the two high-speed sections. Alright, so here's the two high-speed sections compared to each other. Oh, let's go here. Didn't want to include double count it here, but yeah. So hopefully that is a helpful diagnostic tool for you. The other way that we can use this is we could have a shaker running a test or some other kind of live test that we're running. And we could have a benchmark line like this northbound high speed, and we could run our test until we see that the fatigue damage has crossed this benchmark line, and at that point we could make a determination that we've tested for enough time. So the other thing we can do with fatigue damage is convert the fatigue damage spectrum over to a power spectral density graph, which we can run as a random test. So I'm going to go and analyze the whole lap of data here. As you can see, when I analyze the whole lap, our fatigue damage fills all the way up. Alright, I'm going to delete some of these ones that are old. Okay, so I'm going to add in a new graph. This is a FDS test spectrum. And this is where we can convert the fatigue damage spectrum over to a power spectral density graph. But in doing that, I'm going to say that this 2-minute 9-second recording of one lap around the track, I want it actually to have a target life of let's say 100 hours. So let's say as a manufacturer, I'm going to say I expect this vehicle to be warranted for 100 hours of track use. And then I'll test this 100 hours worth of damage in a period of 10 hours. Okay, so this is now the accelerated PSD for one lap around the track times multiplied out to 100 hours worth, and then again multiplied so that I can run that 100 hours in only 10 hours. So now what I do if I want to run a vibration test on this is I copy the graph and I go to Vibration View and I create a new random test. And then I paste. So now my random profile that I created from a lap around the track and then accelerated it to be 100 hours worth of going around the track is brought in as a random test that I can run. So there's that. Next, let's take a look at this firearm burst again, and we're going to talk about shock response spectrum. The shock response spectrum is similar to FDS in that they both use single degree of freedom oscillator filter banks at each analysis point. The difference between the two is that shock response spectrum is kind of sort of do a peak hold at each of these points, and its unit is acceleration rather than damage. What we use shock response spectrum for typically is to analyze shock type events. So I'll illustrate that here. So this is obviously a shock event. This is with the gun firing. And I'm going to make a copy of this. So this is the first pulse. And then here's the second pulse. You can see it's pretty close to the first one, but it's a little bit different. And here is the third one. Hold on. Copied a little bit more than I wanted to there. So I'm just selecting the trace I want to copy and then pasting it with Control V. And the fourth. Okay, and this. So I'll paste that there. So that's all 5 independent ones. Now what's pretty interesting is if I take and analyze the whole block of them. If you look at this trace now, analyzing the whole block worth, it's basically doing an envelope over the top of everything. And that makes sense. That's, to me, what the shock response spectrum is supposed to do. And here I'll play it back for you, and then you can watch it build over time. Okay, so that's the shock response spectrum, sort of doing a peak hold over that range of firings there. And then what we would do with the shock response spectrum is we can create an equivalent vibration test meeting this SRS demand. One thing that we could do is we could take multiple SRSs and do an envelope on those to get the worst case of multiple recordings even. So just bear with me, pretend that this scope in the Y direction is actually a second SRS recording, a completely different one, maybe of like a different firearm, but I'm making one scope that's going to go on multiple weapons. So what I'll do is I'll get the SRS of these two, and I'll get the worst case. So this is where we're going to make use of a new feature called math traces. So I'm going to do the max of these two traces. So to do that, you add a math trace, go to functions, and this gives you the list of all the functions available, and there's quite a few of them. But what we're going to do is use the max function, which is right here. And we're going to take the max of scope Z and scope Y. I'm going to make this a little bit thicker for us so we can see it easier. So now I have a worst case envelope of both SRSs. And it's live updating, so I can move anywhere here and you can see it recomputing. Alright, so what I would do with this combined worst case SRS is I'd copy it to the clipboard, and then I'd go to vibration view, and then add a new SRS test, and then paste this in. So this is brought over from ObserVIEW, remember. And then I go to SRS tab, and the type of waveform that this looks like is actually a damp sine wave when you have a firearm burst. So I'll set that, and then I'm going to do exceed that by 10%, synthesize, iterate, and what I'm doing here is trying to make sure that my SRS that I'm synthesizing is meeting or exceeding my SRS demand line. And here is what the pulse it's going to play looks like. So it's kind of like a burst at the beginning, and then it damps out over time, kind of like a gun firing, and then it oscillating and damping out. Okay. Now I will try to play this back, just for fun, but I'm going to have to run it at like 10%. Okay. And we'll set this to 1. And then we can run it. So that's going ahead and creating an equivalent SRS, 1/10 the level of the real one, because I can't play it back on this virtual shaker due to not being able to play back 400 Gs. That gives you an idea for that. So that is how we can take an SRS of real data, envelope it with multiple traces, and get a worst case, and then run that worst case SRS as a SRS test in vibration view. Let's also take a look at doing some math traces on PSDs in this Gingerman Raceway file. So it would be pretty nice to do, let's say, an average. Let's take an average. So I'll close these graphs. And let's add waveform, and let's add a PSD. And I'll bring up the map again. Actually, on the map, if you go to general settings, we can say open this in the main window, which makes life a little bit easier. So I'll do that now. Okay, so we have this, and I'm going to say, let's take an average, all the traces on the PSD. So we'll add a math trace, and the average will be just this plus this and this, and then divide by 3. And we will again change this, be a little bit thicker, and make it stand out. And now you have a live updating average PSD of all the channels. And we can go through and change different parts of the track and see that average PSD change over time. I can also change the number of lines, and everything updates, so that's pretty neat. I could also bring in pasted traces, let's say from another file, and I could then create an average PSD from multiple recordings. I won't do that here, but just know that the math traces are pretty flexible. You can bring in data that has a different number of points than the PSD does, and it will still work using log-log interpolation. It's a pretty smart feature, so you can bring in lots of different sources, do math on them, envelope and average, and it's very robust. And then at the end of this, what we want to do is then copy this, and then go to vibration view again, create a random test, and paste it. And there you have it again. We have a PSD average of multiple channels brought into a random test in vibration view. So that is all I have to show for the new practical uses for ObserView's features. There's a lot of features I didn't cover today. You can see them in this What's New section here. I'll go through some of the ones I didn't cover. I didn't show you the batch file processor, so that is a pretty useful tool for quickly converting files between one file type and another, or resampling all files to be the same sampling rate, or applying filters, things like that. You can also overlay recordings using this tool, so you could add additional channels to one recording. You can overlay the channels. The software now automatically checks for updates. Doing reports is a little more consistent now. There's now support for a 5 Hz GPS receiver. The current GPS that we have available is at only 1 Hz for updates, and the new one at 5 Hz is quite nice. We have math traces for frequency graphs, as I showed you. I will show you this one quick because it is actually extremely useful. You can do filtering now on the time waveform data without having to export it first. There's also an average FFT, and you can now view all graphs as 3D in preview. So let's take a look quick at applying a filter. So if you click on a time graph, like this one, we can enable the low pass filter or the high pass filter. I'm going to turn on a low pass filter at, let's say, 50 Hz. Okay, so you can see I have a knee in the data around 50 Hz, and it slopes down, And also in the time waveform, you can see that a lot of the high frequency content has been filtered out. I can turn that back off, and then everything returns to normal. And of course I can do the high pass filter also. So I can put a high pass filter at 50 Hertz, let's say, and then that will put a knee in the data at 50 Hertz and start to filter and remove out the low frequencies. It is pretty practical to put in a filter at 3 Hertz for the same reason that we wanted to use a integration corner frequency on the AVD conversions of about 3 Hertz for most IEPE accelerometers. That's all I have to share today. Remember, the download for the software is in the chat, along with a trial license that you can use that has all the features enabled. Thanks, and have a great day.